Okay, so up next we have this sequence here, minus 3 to the n divided by ln. So this has an alternating sign on it. The sign is alternating, so when n is even, this will have a positive sign because of the minus 3 to the n. And when n is odd, this will have a negative sign. So before we worry about the sign, right? Before we worry about that, let's just ignore it to start off here and see what's happening without the minus sign. So we're going to ignore the sign to start. And that means we're just going to look at the other part. So limit as n goes to infinity of 3 to the n over the ln of n. Okay. So we worry about that first. And then if we get an answer for that, then we bring in the negative sign, the alternating sign, to help us decide whether or not the overall one is going to go to infinity, or go to infinity or not go to infinity. Okay, so we worry about this first. Then we'll worry about the negative sign afterwards. Okay. So this, actually I should have said x, not n. I'm sorry about that. I should be going with the underlying function, not the n function, but the x function. So it should be 3 to the x over ln of x. Okay, and here we have infinity over infinity. So we'd like to do the derivative. You might not remember how to do the derivative of e to the 3x. Or, I'm sorry, 3 to the x. So here's the idea, that if you have something raised to the x power, some base raised to the x power, like our 3 to the x, turns out we can actually always turn that into an e function by writing that as e to the ln of b to the x, which actually simplifies to e to the x times ln of whatever the base is. And so that's because e to the ln, those cancel out, you get back to b to the x. But here I'm just using the properties of exponents to write it as an exponential function. So I need this in terms of e so I can actually talk about its derivative. So the limit as x goes to infinity of e to the x ln of 3. Ln of 3 again is just some number divided by ln of x. Okay. So now that I have it written as an e function, I can take the derivative. So that would be limit as x goes to infinity of the derivative of that, which would be e to the x ln of 3 itself, right back to itself, times the derivative of its exponent, which would be ln of 3. All of that is over the derivative of ln of x, which is 1 over x. So cleaning this up, we have limit as x goes to infinity of x times the ln of x times the ln of 3 times e to the x ln of 3. Okay. Well, as x goes to infinity, x goes to infinity. As x goes to infinity, e goes to infinity. So we have infinity times ln of 3 times infinity. This whole thing goes to infinity. So the underlying sequence definitely diverges. And when we now go back and say, what about the alternating one, the alternating sign there? Well, since this is going to infinity, what's going to happen is this is going to go really big in the positive, then really big in the negative. Then it's going to keep alternating back and forth. So because that goes to infinity, this one and diverges, the alternating one would also diverge. So it's also going to diverge. The only way an alternating one would converge is if the underlying sequence went to 0. Then the alternating wouldn't matter. So if the underlying one went to like 8, then that would mean that the overall sequence would be getting closer to 8, but it would keep alternating between stuff close to 8 and stuff close to -8. And so therefore it would diverge as well. This time, since the underlying one diverges, the whole thing is going to diverge. Okay. Let's look at one more. This is actually a quick one here. Sequence n squared over 2 to the n. This is a polynomial, n squared, over an exponential 2 to the n. And we know from our previous knowledge, and we can leverage that here, that, hey, this thing is simply just going to go to 0, right? Because the exponential is going to outperform the polynomial. We could use L'Hopital's rule to show that directly, but here I'm just going to use my knowledge of what we talked about before with growth rates, right? That is that exponentials are far and above any polynomial, any power function. So I'm just leveraging that. I could have really used that same idea with the log being at the bottom to realize that the exponential would way outperform the log, but I wanted to actually work through that example there.